Hello, everyone.
Bonjour.
Bonjour.
Hi.
We are going to tell you all today about Google Dataflow, which is the new open model for batch and stream processing.
Yes, that is us, getting ready for this talk. We were preparing this presentation until the very last minute, and we're super happy to be here. I'm here with Sara Robinson, my colleague from Google. Can you tell?
Bonjour, je m'appelle Sara, je parle un petit peu français. J'habitais en San Francisco. J'aime Swift, la langue, et aussi Taylor Swift. Et j'aime Harry Potter, le livre.
Yes, je ne parle pas français, excusez-moi. But I come from Chile, je suis chilien. I work at Google. 5 years ago, I joined Google as a software engineer, but now I'm a developer advocate. We're in the same team, same as Ray here, that you may know him. He's talking later about Kubernetes, and he already gave a talk on unikernels. But today we're going to talk about data, data flow, streaming data. Who knows about Dataflow already? Yeah, awesome.
People.
Who knows about Apache Beam? Perfect. Okay, so you might know more than me, but I'm very glad that you are all here. BigQuery? Who knows BigQuery? Good. Okay, so you know SQL? Excellent. Perfect. I'm in a great place. So things we're going to talk about today, the road to Dataflow, how Dataflow came to be. We are going to, Sarah is going to show us what Dataflow is. We're going to do a live demo, something we coded together, and looking into what is Apache Beam, what's the future. So let's start with the road to Dataflow. Here we can see a lot of papers that Google has published among the years. Highlighted here is the MapReduce paper. This one is the one that started this whole new way to see data, new way of how to process data in parallel, have as many computers as you need, instead of having one big ass computer. Just parallelize your problems and reduce them in parallel. So if you have lots of data, instead of treating everything together, when problems are parallelizable, you can just get many computers processing each segment of data. And that is cool. That's the map step. But then if you want to get results, if you want to bring things together, count, for example, you will use the shuffle step to bring things together by key and then reduce to get the results you want. This is the basic elements of MapReduce that got implemented outside of Google as Hadoop. You might know Hadoop too. And then our life, the Google path, continued on a different road than the outside world. In 2010, we published this new paper, Flum Java, looking at how all of our MapReduces were getting very complex, chaining them, optimizing these processes, managing them going up, going down, etc. And with Flum Java, we were able to go back to simple statements. Let me read this slide. Flum Java is an easy and efficient MapReduce pipelines. So with a high-level API, with simple data processing abstractions, you were able to focus on what you want to do with your data, not on the implementation details. So you basically define a graph of transformations that is transformed automatically in an optimized series of MapReduce. You code what you want, the system takes care of translating it into MapReduce and optimizing it. This is a very simple example. If we were measuring the temperature of this room, if we had sensors all around this conference center, we might end up collecting data, raw data. And to treat it as parallel, we will have a P collection. That's the basic of Flum Java, a parallel collection. And we have all of our raw data. We point to our raw data there. The second code line is just mapping this. We are taking the first collection, and we are applying a parallel do. Let's do something in parallel to these elements. This is our basic code to key every element of raw data, give it a key, the name of the sensor, and take the temperature. Then if you want to get the mean temperature for each room, that's the third step. That's where we are doing our P collection. So we are taking our parallel collection of maps and applying the mean for this number, but per key. And then we just write out to wherever we want to store this data. The nice thing about Flume Java is that when we write this kind of code, we are not really executing it. It's deferred until execution time. And at execution time, our runner will look at this construction and parallelize it, optimize it, and see how many map reducers you really need. Sometimes you can merge things, sometimes you can split them. But you leave that kind of worries to the system. Then we started using this to process data, lots of data, lots of data. And you start looking at things by day, so you start splitting, for example, what was the temperature of this room for each day. And this is how we process batch data. We need stopping points. We need to say what was the temperature for each day. And that has some problems. Latency is one. When can we know the mean temperature for today? We have to wait to collect all days data. And then even more, because we don't know, sometimes we get late data. As data is being created, it takes a long time or short time to get to the system. So latency is a problem with batch data. Other type of problems you have with batch data are sessions. Sometimes you cannot define a time-based window if someone is playing a game, if someone is going through your store and you want to know what's the average number of elements that each person in my store looks at. That is not bounded by days. Things get split through days, so we want better ways of windowing our data. And we just get lots of continuous and unbounded data, and we need a different way to look at this. One solution that a lot of people used to be the state of the art, the Lambda architecture. Let's have two systems. One system is our batch system that is always correct, that has all the data. But if we want to get data results as they come, we can have a streaming model that processes everything. But then that kind of streaming models are not correct always. Sometimes they are missing data. Sometimes they have approximate results. But that's OK. We can live with approximate results if at the end of the day, we get our batch results. But we can do better. In our case, for the streaming side, we published the Millwheel paper. That's our system that, again, has a direct acyclic graph of transformations, and this framework processes, manages the state and persistent flow of elements. But in this case, we are looking at, for example, how we take streaming data and we filter it. At any time, we can apply our filter and just let some kind of data pass. But when we have this kind of data, streaming data, incoming data all the time, we need some strategy to deal with, hey, how often do I want results? And that's when you bring windows into the system. Do we want to window the data by time, by hour, for example? And that fails, and then you have to look for solutions when you start caring about when data was produced versus when you receive it. In that case, for some data that you receive at 12:30, where do you process it? In the window where you just got the data, or you put it back on a window that already happened? And same here, how do you deal with sessions? Millwheel allows us to deal with sessions and forget about these specific time boundaries. We are going to go deeper into this in the next part. And this brings us to our basic thinking model here, that we have event time. And in a different dimension, in parallel, we have processing time. And there is an ideal state where we can process things at the same time as we are receiving the data. But there will always be a skew. There will always be some time between when data is created to when data is processed. And that's when we define our watermark. We will come back to that concept. Because the watermark defines when we think we are done with some slice of data. Where are you looking at? Do you want to see the result for the last hour? The watermark is how we think of this is when we got all the results we were expecting for this last hour. It might be correct, it might be incorrect. There is a perfect one, but we are not always there. If we are too slow, we will have to wait a long time to get our results. If our watermark is too fast, then we will get data out of time. And we're going back here in a few. So we have these two problems, streaming problems, batch problems. Sometimes you want complete results, so you use a batch system. Sometimes you care about getting results now, for example, cost controls. You use a streaming system. Cost is always important, and that allows you to decide, do you want streaming or batch? Or do we want to have both together? Can we unify both into one system? Maybe Sara has the answer for that.
Yes. Thank you, Felipe.
Yay.
So as Felipe mentioned before, developers had to make a bunch of different trade-offs. With Dataflow, you get batch and stream processing in a single API. And so when you're constructing your Dataflow pipeline, there's 4 key questions to keep in mind. The most important is the what are you computing, which means what types of transformations are you going to do on your data? Do you want sums, joins, histograms? So that's the primary question you have to ask. And then Dataflow makes it really easy to write rules to talk about the next 3 questions. So where in event time do you want to process your data? When you're dealing with unbounded infinite streams of data, you want to decide when you want to emit results for a given window. And then you need to decide when in processing time you're going to calculate the results for that given window. And then finally, when you're emitting a bunch of different results for different windows of time, you need to decide how you want to sum up those results. So we're going to go in detail into all these questions. And we will start with the what are you computing, which refers to what types of transformations you're going to do to your data. So you could be doing element-wise transformations, which would be the map in MapReduce. So in this case, you're going to be transforming each element independently of all the other elements. You're going to do something to each element as you process it. And in this case, you would use the pardo, the parallel do, which is a core transform provided by Dataflow. You might also be aggregating data. So you might be looking at multiple keys and grouping them together. In this case, you would use group by key or combine, which are also transforms provided by Dataflow. And then you might want to do something more complex. You might want to do multiple types of transformations on your data, in which case you would use composite transforms. And Dataflow has a couple built-in composite transforms. An example here is, say you're doing some sort of word count processing, so you want to count the number of words in a given document. You would first do a parallel do to parse your text file, and then output each word on a given line. And then you might do a count transformation to count the frequency of each word in that document. And then you do another parallel do, a pardo, to output the results into a human-readable text file. So let's look at this in code. So throughout this section, I'll be using a simple mobile gaming example where we'll have users creating points by, they could be doing anything. They could be clicking cookies, clicking candy, whatever your favorite mobile game is. So in the first example, we've just got raw log lines. Each time an event happens. We've got a p collection of strings. We're just logging data. And then we get a little bit more complex. We do element-wise transformations. So we're creating a key for each team, and then we're taking their score as the value. And then finally, we're doing a composite transformation. So we're summing each team's score per game. And so here's what this would look like in a graph. Each point represents some score event in our mobile game example. And on the x-axis, we have event time, which is the time when the point was scored. And then on our y-axis, we have processing time, which was the time that the event actually is processed by our system. And in an ideal world, as Felipe mentioned, event time and processing time are the same. But we know that in distributed systems, that's not the case. We might have people playing our game on a transatlantic flight, and then their score won't be processed for hours after it's actually occurred. We might have network delays, people climbing mountains, playing our game. Lots of things could be happening. So here we have this 3 is pretty close. Event time and processing time occurred at pretty much the same time, not too much network delay. But then how do we deal with situations over here where this 9 was scored around a little after 12:01, but it wasn't processed for about 7 minutes after that? And if we're processing this set of data, this white line shows the sum as we're adding it up, and then when we hit the top, we get that blue rectangle, which represents our final sum. And this will work great for bounded data sets where you have a finite amount of data. But in our gaming example, people are always going to be playing the game. It's going to be a smash hit. This will be played 24/7. It's going to be an infinite stream of data. So we can't process it all at the same time. We need to decide when we want to process different windows, which is where the next question comes into play, which is where in event time we want to process our data. And Dataflow has a concept called windowing, which is how you handle this. If you've got a bounded data set, windowing is not required. But if you're dealing with unbounded infinite streams of data that's always coming in, windowing is required. And there's different types of windowing that you can specify based on your use case. So the first type of windowing we could use is fixed windows. So we could say we want to sum our results every 2 minutes. Or maybe you want to sum the results hourly, weekly, daily. You could use fixed windowing for that. Sliding windows are another option. So say you want to sum the data every 24 hours. So you want to get the last 24 hours of data, but every hour. So then you would use sliding windows. And then finally, if you want to measure data in sessions, in short bursts of user activity, you could use the session approach for windowing. And so back to our gaming example. Now we're going to add a rule to split our windows into 2 minutes. So we're going to get the results, the score results for each team every 2 minutes. And this is the only rule we need to apply to add that window to our pipeline. And so this is what that would look like. We can see now we're getting, every 2 minutes, we're getting a sum for all the points that were scored during that time. So this is a little better than what we had before because we were dealing with an infinite set of data. But we still have to wait for all the results to come in to emit our final result. So that's when this idea of the watermark comes into play, which Felipe touched on a bit. And so the watermark is basically the system's best guess that it's finished processing all of the data. And we use a concept called triggers to define when we're going to process the results for a given window. And triggers are usually relative to the watermark. So if we were to add something to our pipeline here, we would say we want to trigger at the watermark, which is actually the default in Dataflow, but we've added it here just for clarity. So let's take a look at how we're processing data when we're triggering at the watermark now. So on the left side here, you can see we have a perfect watermark where we process all the data right when it's, we're summing all the data right after it's been processed. But on the right side, we have our heuristic watermark. And so we can see here that we've actually missed this piece of data up, the 9 up there that came in late. It hasn't been included in our results. And if you look in the second window, you'll notice that we had to wait for all the data to finish processing before we emitted any results. It might be nice to add speculative results so that we could sum the 7, 3, and 4 before we get to the final sum for the second window. So we can add some triggering rules to account for this. And these rules would look like this. So this is saying we want early firing, so we want to calculate results 1 minute before our window ends. And then we also want to take into account data that comes in late after the watermark has passed. So every time a new piece of data comes in, we're going to sum the results again. So looking back at the same graphs, let's see how these rules affect our data. And we can see now that we're actually getting the late result of that 9. It's being included in our sum. And then we're also emitting speculative results for that second window to account for data that came in early before our watermark passed. And so the last thing we have to consider, now that we're emitting multiple results per window, is how do we want to handle those results? Do we want a running total, or do we only care about the results since the last result was emitted? So that brings us to our last question of how do refinements relate? So how should we handle multiple outputs per window? So you need to decide if you want to omit the running total, or do you only care about the values that have come in since the last result? So in this example, we will just add up the sum as they come in. And so we've chosen to accumulate the sum of each window as new data comes in. And so just to summarize, we started with classic batch, and we went all the way to streaming with accumulations without having to tweak our algorithm too much along the way. We just had to add some rules to specify how we wanted to handle our streaming data.
Yeah, so the beauty of it, if we can go back to the code, is our logic is in yellow. That's what we wanted to get, and we were able to get into windows. We were able to get early results, late results, specify how do we wanted to these results to relate to each other without changing one line of our code. And that's really the beauty of this model. So we want to give a live demo.
Let's do a live demo.
Let's do a live demo. Let me show you something that is not written in Dataflow, but it's the Wikipedia Live Monitor by another Googler, Thomas Steiner. Here we're looking at everything that is changing on Wikipedia right now. This is live data. I have no idea what is changing right now. And I have no idea, on the top left, what is relevant. Is something changing because someone is just randomly changing it, or is this big news right now? So Thomas Steiner's paper is about how do we find out what's relevant, and for that he designed 3 rules. Do we find more than 5 changes? Are there more than 3 different people editing this page at the same time? And are these changes happening in less than 60 seconds between each change? And so he started grouping these things by clusters, and we start seeing, yeah, some things, yeah, this one doesn't have more than 5 occurrences. In fact, we started running this like 10 minutes ago, and there has been no news yet. I have no idea if there might come news while we're speaking. Usually someone dies while I'm talking, and it really reflects here. It has happened. But our challenge here was how do we code this in the Dataflow model. In this case, this is not done with Dataflow, but we wanted to bring it back to this world.
Yes, so we built a demo to process this data in Dataflow, and we have a little diagram of how it works, and then we'll do a live demo after we explain it. So this is what our app looks like. We are using the Wikimedia data stream. So we're using the same data source that Thomas used in the app that Felipe just showed. And then we're connecting to an IRC stream to get this data. We wrote a little node server that we are hosting on Google Compute Engine in a VM. And what this does is this, every time a new article comes in, we're publishing that article data to a pub subtopic. We'll talk a little bit more about Cloud Pub Sub in a moment. And then once that's posted to a topic, we can subscribe to that topic, and we do that from Dataflow. Dataflow has a couple of built-in sources that you can read from. PubSub is one of them. So we're getting all the updates, and then in Dataflow, we want to store all the historical news data so that we can do some SQL queries and analyze historical data using BigQuery. But then we also want to do something similar to what Thomas did and create a real-time dashboard for the latest data that's happening right now. And we're using Firebase to do that. So.
Oh, PubSub.
PubSub.
Yes.
So we mentioned that we're using PubSub. PubSub is another cloud product that provides asynchronous many-to-many messaging between applications. So you have a concept of a topic, and applications can publish to a topic, and then other applications can subscribe to updates from that topic. And so we're using that to pass the data to Dataflow. And we're doing that on our Node server, as I mentioned before. We're using the gcloud Node client library, which gives us access to a couple of different cloud products through Node. And so it's really easy to publish to a PubSub topic using gcloud. We just say topic.publish, and then we send it the JSON data for the latest article. And it's super easy to read from a PubSub topic.
Yes, same side. If you're publishing to PubSub, then you can subscribe to any topic you would like to. You just, in Dataflow, you just say, hey, read from this one, and if authentication is set up the right way, usually it is, you just start getting immediately a copy of everything that someone is publishing into this channel. We have a slide later about Spotify, how they've used this to publish millions of records. In this case, we're going just 3, 5 QPS per second, whatever people are doing with Wikipedia right now. Right into Firebase at the end of the flow.
Yes. So Firebase, as we'll touch on in the next slide, is a platform for building applications which has many features. We're only using the real-time database feature for this application. So it's a NoSQL JSON database. And my favorite thing about Firebase is that everything updates in real time. So data is synchronized to any connected clients right as it happens. So this means any client that's connected to your Firebase database will see updates right as they happen. You don't have to refresh the page. So we're using Firebase to power our real-time dashboard of news articles being edited right now. And in Dataflow, we write some data on the latest article to Firebase. And this is a snippet of the code that we use to do that.
Exactly. I'm not using Firebase as a long-term storage, but with Dataflow, I can tell, hey, from my collection of clusters, pick the top 10 according to my comparator, the ones that have more changes, give them the key latest clusters, and we publish that to Firebase. And Firebase will find these 10 articles under that key.
So let's take a look at our pipeline.
Yay. Dataflow running on the cloud. This is how we run
Here we
things.
go.
So this is our Google Cloud console. You can see here that I have my VMs, I have my code, I have my Dataflow flows. In this case, this Dataflow that we started running some minutes ago, 16 hours ago. It's been ingesting all the data that comes through PubSub. So basically, in this pipeline, everything begins from PubSub. Oops, I don't want to go back. I want to scroll. And I have different flows here. This one just sets to Firebase whatever is the latest element. And we're getting 11 elements per second right now. And I can see each node, each logic node, how it's performing right now. It's lagging in 7 seconds. It has its watermark. It has seen 30,000 elements. And here we are setting it to Firebase. In parallel, I also sending everything in JSON to BigQuery because I want to store it. But the most interesting pipeline here is how I'm windowing these elements into fixed site windows, giving each element a key, grouping them by key, and then I'm able, on one hand, to run the metrics and send to Firebase the clusters without the filter, or even filter them to see if there are any relevant news while we speak. Can you show the Firebase side?
Yeah, let's see how the data is being stored in Firebase. So this is the Firebase app dashboard, which is where we can visualize all of our data. And we're storing the data for each session under a different node. So as Felipe mentioned, from Dataflow, we're storing the last article in Firebase as a JSON string. Because we're in France, we thought it would be cool to show you the latest French article as well. So every time a French article comes in, we save that. And then this data under latest clusters are articles that may be meeting some of those conditions we mentioned and may qualify as breaking news. So let's take a look at the dashboard. This is what it looks like. So this is just a simple JavaScript application that's reading from Firebase, and it's displaying the latest article that's being edited here. Every time a new French article comes in, we see it on the right. And then here's where we see all of our clusters. And if they're meeting any of those conditions, we'll see a check mark in one of those boxes. And we don't have any breaking news yet. But this is how we're displaying all the data as it comes in from Firebase.
So we're able to subscribe to a data source, pipe it into a data flow we define. Each step is, where did I?
Oh, Dataflow.
Yes. I can define each step in a logic way, and then the system takes care of how we run it. I don't really care if all of this is running on one server or 100 servers if needed. The system will take care of this in real time, scaling up, scaling down, and looking at the number of elements I end up having, all coming from this collection. And I can end up visualize them, store them in long term, and it's really, really new, easy way of thinking of streaming data.
So Firebase is great for displaying the latest articles that are coming in right now. But as Felipe mentioned, we might want to store all the article data and do some queries on that. And for that, we will use BigQuery.
Oh, yes. I saw some hands for BigQuery. If you don't know BigQuery and you like working with data, you should know about it. It's fast, the fastest thing I've seen. It works with SQL. It's scalable. You don't have to invest money in it. The costs are only about how much data you have and how much data you're querying. There are no servers to take care of. It works with Tableau, R, Python. If you want to share data with other people, it shares data with other people. In fact, I share a lot of interesting data sets in BigQuery. And everyone can query it for free with a free monthly quota. In this case, I've been storing all the, where is my BigQuery? Here. I've been storing all of the change logs for a couple months. So where are my objects? Yes. So basically here I have 40 gigabytes of changes since January 13, 100 million rows. And each row looks just JSON. I'm storing the raw thing. And I can easily define a view over this that runs in real time. That's basically extracting, using JSON to extract each column, the title, if it's about the server URL, etc. And here I have a query that I'm using to test our algorithm. So even though Dataflow merges stream and batch, there's still some use for batch when you can do things really, really fast and test your theories. In this case, this query will look at my table at the last 26 days, things that are not edited by bots. And I'm looking for all the changes, all the pages that have more than 100 changes with more than 20 editors, and I'm ranking them and getting the top article according to these rules for each day. And it's really interesting to see what was the top news yesterday. Doris Roberts, the Equator earthquake that had 50 editors and 200 changes the previous 2 days. This is the Japan earthquake, Kobe Bryant. And you can start looking at real data, understanding that, yes, Wikipedia changes really reflect what is happening, and you can go deeper and querying these kind of things in a real short time. In this case, my query was catch, but it took about 15 seconds to go about these 50 columns. And I could not talk about data at Google without showing you a little of BigQuery. March 3rd, there were a lot of changes to this page that was ultimately deleted, but a lot of people were talking about Trump. Yeah, it's just a fun way. If you want to see only the changes to France, you can see this. I don't know what Boutros Ghali is, but you can just start going back in time and looking at this data. Let's go back to our talk. We have 12 minutes left.
So we showed you a demo that we built using Dataflow, but it's also cool to talk about some companies that are using it in production, and Spotify is one of those. How many of you use Spotify? Looks like a lot of people. Yeah. So Spotify is using a bunch of different cloud products. They are also using Dataflow. So they use Dataflow to capture any sort of events on the client. So an event could be somebody clicking listen on a song, somebody searching for an artist. They're keeping track of all these events. They're passing them through Cloud PubSub and then using Dataflow to persist those in a Hadoop file system and then also to Google Cloud Storage. And if you want to read more about how they're using Dataflow, there's a bit.ly link here, bit.ly/Spotify Dataflow. They've got a couple of blog posts that go into detail on their whole architecture.
And they have way more data than my Wikipedia pipeline. So it's really cool what they are doing and how they are sharing their learnings through while they go through this.
So
next steps.
What is the future of Dataflow?
Future, yes. Is it still called Dataflow, and why I'm talking about Apache Beam? So Dataflow has these two legs. One is the Dataflow model. It's a programming model that it's a really interesting way to process real-time data, batch data, unified model. And we also have the runner that we saw running our process and doing everything without us managing any servers. And the Beamflow model, the Dataflow model, it's the state of the art right now in many ways. And a lot of people want to adopt it. And in order to adopt it, we tried open sourcing it, and that was well received. But to really adopt it, it needed to be part of Apache in order for other projects to be able to depend on it. So we did that step, and now the Dataflow SDK model, it's called Apache Beam. There will be no Dataflow SDK in the future, just the Apache Beam model, and the Google Cloud Dataflow as a runner. And the Apache Beam goal is to support multiple runtimes, multiple languages, and you will be able to find there first the model we just explained today, the what, when, what, where, when, and how of streaming data. Different SDKs for writing Beam pipelines. We saw the Java one, the Python one is almost there. Spotify is writing their own Scala run SDK. And you will also find different runners. You have the Google Cloud runner, we have the localhost runner, and also Data Artisans is writing the Apache Flink Dataflow Beam runner, and Spark is getting, thanks to Cloudera, the Apache Spark Beam runner. So you can see this whole technical vision of how we want to cater to different levels. End users, we want to use the Apache Beam model. SDK writers that will bring this model to different languages. And runner writers, how distributed processing environments will be able to run Beam model code. So we have this community. The goal is to collaborate. The goal is to grow and to participate. Apache Beam is now an official Apache project in incubation. The incubation was accepted back in February. Right now, everything is going through chaos as things are moved from the Dataflow package to the Beam package. But as things stabilize, everything will start depending only on Beam. Yes, to go back to our papers at the beginning, it all started for us with the MapReduce paper, and then we followed with a lot of other papers, that Colossus, Bigtable, PubSub, Dremel, etc. And the world implemented them as open source. Spark, Hadoop, Test, Pig, etc. But we now want to change this with Dataflow. We want to unify both worlds with the Apache Beam name. That's our vision for the future. If you want to learn more, there's a lot online. Beam Incubator, Apache.org. You can find the stream of Change of Wikipedia if you want to play with that. We have a Twitter channel. You can find me and Sara online. We love Twitter. And we love feedback. If you like this talk, please give us your feedback. And if you didn't like it, please explain us why, because that's how we learn. That's the link for feedback.
Thank you. That's all we got.
Thanks. I have your approval. Thank you. Uh-huh. Yes. Okay. The question is about the compatibility matrix. As we have different runners for one model, we had a slide that we deleted, in fact, because it was a lot of information for one slide of how each runner supports different features. And the feature you're asking about is? Retractions. Oh, yes. We are working hard to bring retractions to the Beam model. Inside Google, do we have retractions? If I give you an answer, I don't know if I should retract it later. So I have to be very careful about that. But yes, retractions are an important part of this model that are not yet implemented in Dataflow or Beam, but we want. Yes, thank you.
Anything else?
Other questions? Are you ready to play with streaming data, live data? Oh, we have a question. Yes, please.
Yes.
Are you looking for particular contributions on the Apache Beam side, or not specifically any area?
Are we looking for contributors on the Apache Beam side? Yes, in fact, a lot of people are contributing already to the Apache Beam side. This is not a Google project anymore. It's an Apache project. And the people signing up for, there are a lot of companies, not only Cloudera and the ones I mentioned. There are a lot of companies contributing, and if you want to contribute, that we would be very, very welcome. Yes. Anyone? 3, 2, 1. We're free. Okay, thank you very much.
Thank you for coming.
Merci beaucoup. Yay.